In this lecture, we're going to look at some historic models for the structure of the atom. And our essential question for this video is, what is matter made of? Really at the smallest level, what does matter look like? And you've maybe seen some models of atoms that look something like this. And I think we'll talk about eventually why that's maybe not a great representation of an atom. So in the 1700s, the way this video will be structured is we'll walk historically through greater and greater understanding of the atom. In the early 1700s, there was some work done by some early scientists that looked at the conservation of mass, that in a chemical reaction, matter is neither created nor destroyed. It's just rearranged. And that was a really important observation because that gave us the idea that this atom might be, that matter might be comprised of atoms and of discrete particles of mass, and we'd be looking at rearranging those rather than fundamentally changing them, which began leading scientists down the path of trying to figure out what those atoms look like. A little bit later on, scientists began looking at the law of definite proportions, which told us that these elements were combining in small whole number ratios to form compounds. And what I mean by that is if we look at some compounds, maybe H2O or CO2, there's 2 hydrogens to 1 oxygen, or 1 carbon to 2 oxygens, and not something like H2.1 to O 0.9, or C 0.3 to O2. And that again was the understanding of those ratios, which were really determined based on the masses of compounds, the relative masses of compounds. Those ratios again gave evidence that there must be some atoms existing as discrete objects at the smallest level. So we'll first turn our attention to John Dalton doing some work in the 1800s. And Dalton came up with a couple of different ideas about atomic theory, or how atoms behaved. He stated that elements are made of extremely small particles called atoms, and that atoms of a given element are identical in size, mass, and other properties, while atoms of different elements differ in their size, mass, and other properties. Dalton said that atoms can't be subdivided, created, or destroyed, which we'll find out is not entirely true, but at the time fit all the evidence that was available. Dalton would also say atoms of different elements combine in simple whole number ratios to form chemical compounds. That's that law of definite proportions from up above. And finally, in chemical reactions, atoms are combined, separated, or rearranged. So here we have 5 posits of Dalton's atomic theory that again fit the evidence at the time. And Dalton thought that atoms looked a little bit like these pool balls here, or these billiard balls, these hard spheres of matter. We then, in sort of the intervening decades and years, 3 scientists went on to make major contributions to particles that comprise an atom at a smaller level. So that would begin to cast some doubt on Dalton's idea of atoms being unbreakable billiard balls. The first scientist we want to look at is JJ Thompson, who was doing his work in 1897. He's an English scientist. And Thomson used something called a cathode ray tube. You maybe heard about cathodes and anodes being involved in electricity, with particles flowing from one side to the other. So Thomson didn't know at the time, but he was actually shooting electrons from one end of this cathode to the other, one end of this cathode tube to the other. And what he attempted to do was to bend the stream of those electrons using some magnets or some electric currents. And Dalton went on to find out that in the presence of a magnetic field or electric field, he was able to bend this stream of particles. And that gave him some clues that what he was looking at was a negatively charged component of an atom. And this was really some of the earliest evidence that an atom could be broken down into smaller parts. So Thomson came up with what he called his plum pudding model of the atom. And in this, Dalton thought that these small electrons, or he called them corpuscles, these small electrons were stuck all over a large positive charge. Again, that fit all his evidence at the time, and he thought he'd be able to pluck an electron off of the positive charge, send it through the cathode tube, and bend the path of that electron. The electrons, when we understand them now are what exist around the outside of a nucleus of the atom, or in the electron cloud of an atom. They take up most of the volume, but very little of the mass. And again, thanks to the work of JJ Thompson, we know electrons are negatively charged. A scientist named Millikan would go on to discover the mass to charge ratio of an atom, and therefore the mass of an atom, or excuse me, mass of an electron, but I'm not so concerned with that experiment right now. It's also interesting to note that JJ Thompson's cathode ray tube was what was used in old TVs. Old TVs that are called CRT TVs, the big boxy kind. That's a cathode ray television or cathode ray tube. And that stream of electrons can be bent using some magnets or some coils. And depending on where it's bent to, can excite different pixels on a screen. And that process happens real quickly. So this electron gun in the back of a TV can trace its path across a television screen, exciting pixels one at a time and creating the images that we used to see on televisions. This is not how modern televisions work, nor did JJ Thompson invent the television, but just an interesting application of a scientific research device for entertainment. The second scientist we have is Ernest Rutherford. He was originally from New Zealand. He did some work in Montreal, Canada, and then he went on to work actually in the same lab as JJ Thompson in England, the Cavendish Laboratory. Ernest Rutherford set up a famous experiment known as the gold foil experiment. In this, he shot a radioactive series of particles. We now know them as alpha particles, which are just small, dense, positively charged particles. But he shot those alpha particles through a sheet of thin gold foil. And Rutherford was expecting them all to pass directly through. He sort of assumed these alpha particles were sort of like a shell from a naval ship and was going to punch right through a sheet of tissue paper. And had JJ Thompson's model of the atom been correct, that's exactly what Rutherford would have seen. So Rutherford and his several assistants began counting the number of particles that hit on different parts of this fluorescent screen. They just sit in a dark room for hours and just count. And lo and behold, most of the particles passed almost directly through or were deflected slightly, but some were deflected really dramatically. And nothing about JJ Thompson's model of the atom could explain why those particles were deflected so dramatically. That clued Ernest Rutherford into the fact that there must be a different model of the atom that more accurately represents how it's truly arranged. Here's just another view of the gold foil experiment, again showing the sort of the viewing microscope that had to be set up in the dark, and these scientists could only look for maybe an hour or two before their eyes would become exhausted at the strain of doing this. Seeing the radioactive source that's going to send out these alpha particles. So the model above is what JJ Thompson, or what would have been predicted had JJ Thompson's model been correct. These dense alpha particles would have punched straight through the plum pudding model. And in reality, most of them did, but some deflected back. And Rutherford surmised that only could happen if all the positive charge were concentrated in a very small, very dense nucleus. So Rutherford took this big positive charge of JJ Thompson and he shrunk it down into a small nucleus. And that allowed most of the alpha particles to pass through the electron cloud entirely undisturbed. But some, very few, hit the nucleus dead on and deflected out at extreme angles. While he didn't know it at the time, what Rutherford had found was a nucleus comprised of protons and of neutrons. In a later experiment, Rutherford would find the proton, so we'll give him credit for it here. Proton is a heavy particle. It's heavy. It's something like 1,800 times heavier than an electron. It's positively charged. It's found in the nucleus. We now classify elements based on how many protons they have, where our first element, hydrogen, has 1 proton. Our second element, helium, has 2 protons. Our third element, lithium, has 3 protons. So the number of protons determines our element. One particle left. James Chadwick worked a little bit later than the other 2 scientists. He was another English scientist working in the 1930s. And Chadwick set up an experiment where he shot alpha particles. That was the same particle that Rutherford used. Shot it at a sheet of beryllium. And those alpha particles, he thought were dislodging something or knocking something out of the beryllium, but he wasn't sure what it was because he couldn't manipulate them. And if you can't manipulate something, it's hard to tell whether it's there or not, especially when it's as small as these subatomic particles. But what Chadwick did find is that whatever it was coming out of the beryllium was able to knock protons out of a sheet of wax. And those protons could be detected and could be counted. So again, Chadwick shot alpha particles at beryllium, something happened, something came out of that beryllium, and that something knocked protons out of paraffin wax. What Chadwick deduced from this is that there must be a neutral particle or an uncharged particle of near equal mass to a proton. Because it was neutral or uncharged, he called it a neutron. So the neutron, like the proton, exists in the nucleus, has a mass very similar to a proton, and is uncharged. Those 3 experiments I would like you to know moving forward in this course. The cathode ray tube experiment of JJ Thompson, the gold foil experiment of Ernest Rutherford, and finally this paraffin wax and beryllium experiment of James Chadwick. I also want you to be able to link each experiment to the particle that was discovered. For instance, Thomson shot a stream of cathode rays through a cathode ray tube and used that to determine some properties of the electron. Ernest Rutherford deflected alpha particles off a sheet of gold foil to determine there had to be a nucleus and later a proton. And James Chadwick discovered these heavy, uncharged particles known as a neutron. I think it does warrant mentioning, though, that there's still a little bit more to be said about the structure of the atom. A scientist named Antoine Becquerel in 1896, he was a French scientist, discovered something called radioactivity. And he deduced that atoms must be breaking down and releasing some particles due to radioactive decay. We now know 3 different kinds of radioactive decay: alpha particles, beta particles, and gamma radiation. And that's just a little bit of a preview of things that we might touch on later throughout the course. But I think it's important for you to recognize that these atoms can in fact be broken down and do in fact break down often, or from time to time. What we'll look at next is the work of Niels Bohr and a lot on the arrangement of those electrons. Thanks for watching.